tells you that it is a relation. Even though you have the same y values, remember, it is okay to have the same y value. So this actually is a function. Okay, next we have this right here, and this is a red flag because they're telling us is 1 gives you 8, but then they're also saying if you plug in 1 to this function, you get out 10. That doesn't work. So this is simply a relation. Now this is a little easier to tell if you're working with graphs. So if we look at our next set of examples, we have this test called the vertical line test, which sometimes you'll see abbreviated as VLT. What that tells you is if a vertical line intersects a graph more than once, it's not a function. So let's go ahead and take a vertical line and put it through the graph. Now notice this vertical line only touches right there. And if we would slide that line across the entire graph, notice it's only crossing the graph at one point. That then passes the vertical line test, and we can say that this is in fact a function. Let's try it on this second graph. So if we pass our vertical line along this graph, notice it's only touching at one spot anywhere on that graph. So again, we can say that this is a function. Now lastly, if we take our vertical line and pass it along this graph, notice that as I'm passing it along, it's not just crossing in one spot because it's crossing right here and it's crossing right here. So again, if it crosses the graph more than once, it is not a function. So we cannot say this is a function. It's simply a relation. All right, so main thing there is if a function has points that are directly above or below each other, or if the graph does, then it's not a function. So let's try that again here. Let's get another vertical line. We're going to see if these sets of ordered pairs create a function or a relation. So if we pass this vertical line along in our first graph, that only hits once there, once there, once there, once there, once there, and when we get here to an x value of 4, notice I have this and this. So that is going to fail the vertical line test because they're saying if you plug 4 into this function, you might get a positive 2 out right here, but if you plug 4 in, you might get a negative 4 out. So that's not a function. That is only a relation. So let's go ahead and try it on our second graph. All right. I don't know where my word went, but that was a relation because it did not pass the vertical line test. So now let's take our vertical line and pass it through our second graph here. So we got 1 point there, 1 point there, 1 point, 1 point, 1 point, 1 point there, 1 point there, and lastly 1 point way up there in the upper right hand side. So notice that that vertical line, only 1 point touched it anywhere we passed it through. So this second graph is in fact a function. All right, so only 1 point can touch that vertical line in order for a graph to be a function. So that moves us into whether or not an ordered pair is a solution to a function. So we're going to be talking specifically about functions for the last part of our notes. So an equation in two variables is usually the types of equations that we'll work with in algebra. They have an x and a y. So something like y equals 3x minus 4. That's an equation in two variables. To determine if something is a solution to an equation like that, you have to plug in for x and y and see if it makes a true statement. So we're going to figure out, is 2 comma 5 a solution to that equation above, y equals 3x minus 4. So we're going to plug in 2 for x and 5 for y and see if that gives us something that makes sense. So if we substitute, we'll get 5. We want to see, is that equal to 3 times 2 minus 4? So is 5 equal to 6 minus 4? And we can see no, because 5 does not equal 2. So no, 2 comma 5 is not a solution because it made a false statement. One more thing that we will mention from time to time are these things called independent and dependent variables. The independent variable are your x values in an equation, which remember we called those our input values. So independent is input and dependent is your y's, those are your output values. All right, so let's look at some graphing of these functions. So we're first going to look at this graph of y equals 3x minus 2. So to graph an equation, you simply plug in your inputs, your x values, and see what you get out for your outputs, and then you can plot those points on the coordinate plane. So let's do y equals 3x minus 2, and we're going to substitute in this negative 2 there. So y equals 3 times negative 2 minus 2, which is negative 6 minus 2. So we can see when we plug in negative 2, we get an output of negative 8. Now if you were going to go ahead and do that for the next 4 ordered pairs, if you plug in negative 1, you should get negative 5 out. If you plug in 0, you should get negative 2. An input of 1 will get you an output of 1, and an input of 2 will get you an output of 4. Now that you have those inputs and outputs all filled into your XY table, we just have to graph those. So our first ordered pair, negative 2, negative 8, we're going to go to our origin, go 2 left, and down 8. So your first point will be way down there. Negative 1, negative 5, go left 1, down 5. 0, negative 2, over 0, down 2. 1, comma 1, right 1, up 1, and 2, comma 4, right 2, up 4. So if you notice, those go in a straight line, which they should. So we're going to go ahead and draw a line through those points, and that would be a graph of the equation y equals 3x minus 2. Okay, so one last thing that we need to talk about is the different kinds of equations. So the first that we're going to talk about, which we've talked about a lot so far, are these linear functions. And those are always in the form y equals mx plus b. And they always have an exponent of 1 on the x variable. And the graph is going to look like a straight line. So if we would have our y and our x plane, this would be an example of a linear function, straight line. We're going to talk about quadratic functions a lot this year, and those are in the form y equals ax squared plus bx plus c, where your x has an exponent of 2, and this graph is going to look like a U. It's a U-shaped graph, which if you recall, we call a parabola. So if, again, we have our x-axis and our y-axis, a parabola would be this kind of shape. And that is called a quadratic function. All right, so if we take a look at one more thing here, this function notation, really the only thing you need to know about it is that instead of y, we use this f with x inside parentheses. So how we would read that is f of x equals 2x plus 3. Okay, and it is really useful. So like if we look down at this example below, if x is 5, then f of 5 would equal 2 times 5 plus 3. So f of 5 is 13. Okay, so that's pretty useful because we know if we plug 5 into the function, we would get an output of 13. Now, if we weren't using function notation, we would just write y equals 13. Well, I don't know what value for x was plugged in to get that y value. Function notation takes care of that because you know you plugged in 5. So let's practice using that in a couple of examples. We're going to say f of x equals 4x minus 8. So let's evaluate that when f is negative 2. F of negative 2, we need to replace all of the x's in the function with negative 2. So we'll have 4 times negative 2 minus 8, which is negative 8 minus 8, and that's going to give us negative 16. So for this function, f of negative 2 equals negative 16. Now I encourage you to pause the video and see if you can do the next two, f of 3 and f of 0. So pause the video now. Okay, so hopefully you got a chance to practice those two. When you did f of 3, you should have found an output of 4. And when you did f of 0, you should have found an output of negative 8. All right, so if you did those correctly, nice work. If not, just go back and make sure you correct those mistakes. And our final example for today, we're going to graph the function f of x equals x squared minus 2x plus 1. So you notice we have a power of 2, which is going to make this a quadratic, and our graph better look like a parabola when we're done. Let's plug in the first point together. So f of negative 3 means we're going to plug in this negative 3 everywhere we see x. So we'll have negative 3 squared minus 2 times negative 3 plus 1. If we evaluate that, negative 3 squared is 9. Negative 2 times negative 3 is positive 6 plus 1. So 15 plus 1 will give you 16. Okay. So I encourage you again to pause the video and evaluate those other 6 x values. See what you get for y. So if you would like to pause the video now and give that a shot, you are more than welcome to do that right now. So if we just go ahead and plug in what you should have evaluated, when you plugged in 2, you should have gotten y is 9. When you plug in negative 1 to that function, you should get an output of 4. 0 will give you an output of 1. Notice that's this right here. It's kind of like the y-intercept. When you plug in 1, you should get 0 out. When you plug in 2, you should get 1. And when you plug in 3, you should get 4. Now let's graph those. This first ordered pair you probably won't be able to fit on the graph because 16 is way too far up. So let's start with negative 2, 9. So go left 2, up 1, 2, 3, 4, 5, 6, 7, 8. And it'll be a little off the graph at 9. If we plot negative 1, 4, we'll go left 1, up 4, 0, 1, go over 0, up 1. 1, 0 is right 1, up 0. And 2, 1, go right 2, up 1. And then 3, 4, we will go right 3 and up 4. And if you were to plug in 4 for an x value, you would actually see that you'd get positive 9 out. So notice that those are symmetric, which parabolas always are. And we're going to do our best to draw a nice smooth curve through those points. And that would be the function